is I'm gonna just tell it to start streaming, and then start chatting away, and away we go. Let's do that right now. I say start streaming the event. So today is a live coding morning, and the last couple of times we've done live coding sessions, we've been looking at a feature for raptorjit called sealed tables, and it kind of went pretty quick in the beginning. We got something kind of compiling and working on trivial examples pretty quickly. Then we got a little bit bogged down in trying to kind of generalize it and make it more fancy and deal with metatables and that kind of stuff. So what we're going to do today is scale it back. We're going to actually say that first thing we came up with was potentially something actually quite interesting. So it's worth committing that somewhere, making an actual demonstration out of it to show that there is a problem that it solves, and then making a pull request out of it so that other people can also take a look and check it out and maybe play with it and give some feedback and that kind of thing. And then the expectation is that we're going to iterate on this a couple of times before this would be something that would be merged to any branch, and then probably it would be merged to somebody's private branch, and gradually make its way to the upstream repository. Anyway, let's just review what the problem is, what we've done, and then let's just dive into it. So if I hop over to the oldie terminal, so we made this feature. I'll pull up our first example program. Or will I? Hold on. I'll go into a tmux that should already have our. We're working here. No, here. So we have an example program, seal1.lua. So the idea here was that we have a table we create that contains some constants, and then we have a loop down here that is accessing these constants and doing some arithmetic on them. And what we wanted with the sealing is that we would say, the idea is that we would say jit.sealed-t to tell the just-in-time compiler that this table is sealed, which means that we would like it to aggressively optimize for reads at the expense of writes. So it's going to basically, when we do the lookups in here and it's generating the compiled code, it's going to actually put a constant in the machine code because this table is sealed. And then we're going to take some care to make sure that this happens in a safe way. And we got this program working, and I'm not going to repeat all of that. We got this working so that so this all gets compiled down to just a constant, because this t.x is inlined as 10,000, and then the normal constant folding optimization feeds that and does the square root at compile time, recording time. And the same thing happens over here, and the same thing happens with the multiplication. Anyway, that all just turns into a constant, which is really nice. So, the real motivation for this feature is worth revisiting now. So the reason that I got interested in having this feature from the beginning is that I was feeling a little bit provoked by code like this. So here's one of the standard benchmarks from the LuaJit repository, and I think this comes from a Lua mailing list or something. So I'm not sure what the exact origin is, but this is an implementation of MD5 in Lua. I can scroll down a little bit and see the whole code, but the bit that gets me is this part at the top, where we're going to do a lot of bitwise logical operations and that kind of thing, and you have so much boilerplate. I don't like this. So we need to do XOR operations. We need to do bitwise AND. We need to do bitwise OR. These kind of things, and we need to do shifts. And what we see in the code is that they actually, for each library function we want to call anywhere that's performance sensitive, they declare a local variable, and then they resolve this. They go into that, look up the library module, and then look up the function of that library, and then shadow it in a local variable in this module. And the reason for that is fear that that if you would call bit.bxor in the body of your code, that it might turn into a hash table lookup on a global table, and then a hash table lookup on the function, and just generally do a lot of generally do a lot of work in your inner loops, which you don't want. So this is a kind of very defensive way of writing code, where you just do a lot of boilerplate. And for me, this is not cool. This is like Java programming for me, right? The next step is that you write an editor mode or IDE that automatically shadows every function you call everywhere and keeps the shadowings up to date and everything, and then you're going down the like Java, Eclipse, all the rest of it way. So hell no, we're gonna try and update the compiler so this isn't needed. So then what I did is I updated this benchmark to be like the way that I would prefer to write it, which is only a really small difference, and I'll show you that. MD5 no local. So the difference here is just, well, I mean, these declarations aren't there anymore. I'll just align these a bit better. So the declarations are all gone in the new one, so we're not doing any of this shadowing, and we just call, if we want to do a bitwise XOR, we just call bit.b XOR, and we don't worry about the possibility that this is going to compile into a hash table lookup. And the reason that we don't worry is this new sealed tables optimization. The reason is that when we come down a little bit, we are sealing some tables. So my notion is that basically with sealed tables, basically you would generally seal modules. We might even update the require module loader to automatically seal them optionally or something like that. But anyway, when we say seal the bit table, what that means is that when the JIT compiler is compiling something like this, it's gonna generate it's gonna specialize the machine code on this on the value it finds here at the time that it generates the machine code at recording time. And what that means is that we don't need to do any of that local stuff. It's going to be even kind of more, well, it's going to be very, very specialized, right? The actual, it's just going to treat that as a constant. It's going to make that lookup disappear. And the price that we pay for this is that if we would ever change the bit table, then we're going to have to flush all the machine code and have it regenerated, because the old stuff will be invalid. But the thing is, we're in things like an MD5 benchmark, we expect to be calling these fundamental functions really a lot, maybe a billion times a second or something, like a lot. And we don't expect to be changing them very often. Probably we will never redefine bitwise OR and these kind of functions. So that's the idea. I'm rambling a little bit. And now, in order to make a little demonstration of this and show the kind of the usefulness or non-usefulness of the sealed tables optimization, what I want to do is just a little bit of a benchmark here, just to see what is the performance difference between these two versions of MD5. The one with a lot of boilerplate and locals caching versus the one without any of that. How does each one perform in different situations? Like how does it perform with the baseline versus with the sealed tables in both cases? How is it affected by whether loop optimization is enabled or disabled? And these kind of things. And the loop optimization thing is actually really key. So something that I'm trying to do with raptorjit, which I felt a bit lacking in luajit, is to get robust performance. So not just really good performance, and not just that you can, if you're an expert, tweak a benchmark to go really fast, but to make it easy to get fast code. So what this needs actually is some kind of overlapping optimizations. So the loop optimization, for example, is very, very, very effective when it works. It does a great job, but it's not always there. And when it's not there, you can lose a lot of performance. So what I want actually is some additional optimizations that overlap with loop optimization, and I see sealed tables as something like this. If you're doing the loop optimization and you're optimizing a tight loop, you won't be doing lookups over and over again. You'll just do them once on the first iteration of the loop, and then the compiler will detect that the lookup is loop invariant work, and it won't repeat it. But if you in code that's very branchy and so on, you don't always have the luxury of having the loop optimization there. So then it's very good if you have a secondary way that you can also eliminate those lookups, and that's what the sealed tables is. So I did a little bit of happy testing on this the other day. So I know that I'm expecting it to work in a nice way, but I only did like a n=1. So we're going to do just a very, very slightly more in-depth benchmark. And maybe what we'll do is maybe we'll start off a benchmark running, and maybe it's going to take, if we want to get a little bit of data, I don't know, it'll probably only take a couple of minutes, but we'll kick something off, and while that runs, then I'll come back to the code, because since the last one, since the last live coding session, I did do a little bit of work on the code, and I didn't actually change particularly the little 5 lines or so that we did for the sealed tables optimization. All I really did was add a little bit of scaffolding. Like instead of globally sealing every table, I added the function jit.sealed to declare which tables should be sealed, and this was just necessary to be able to test the feature in real programs where it might not be a good thing to seal everything. Like here, we just want to seal the modules. So let's kick off a teensy weensy little benchmark, and I might even go fishing in my shell history to find one where I've run this before. Yeah. So here's what. So I want to test. But what do we want to test? We want to do a little test matrix. We've got sealed. We want to test the v2.1 LuaJIT, we'll say, because we're doing this based on LuaJIT, and we're going to port this over to raptorjit when we're ready. We're going to want to test the baseline v2.1 against the sealed. These are both these are branches, like software versions. Well, I guess we should make those rows rather than columns. So LuaJIT version is going to be v2.1 versus sealed. And then we're going to also have a benchmark will be MD5 and MD5 no local. And we're also going to test with loop optimization disabled. So, well, which of the scenarios that we're really interested in? So, the most interesting thing, from my perspective, is to test how does it work when we run the de-optimized one that doesn't have the local shadowing. How does that run? And how does it run when loop optimization is disabled? Because that's going to tell us, if you write code like this, how robust is it in the situation that the loop optimization can't eliminate your lookups. So that's measuring what I'm most interested in. And I guess separately we could test with. I don't want to do too many tests. Okay, so what we're going to do is. We're going to have a test with or without loop optimization. Just because it's an interesting kind of thing, I suppose. I guess it's nice actually to be able to compare this table sealing head to head against loop optimization. Because if we're saying that we want loop optimization and sealed tables to both be two kind of overlapping, productively redundant ways of eliminating table lookups, then it's nice to know how they compare. Is one of them actually a little better at it or a little worse at it than the other, that kind of thing. So it is worth throwing loop optimization into the mix. So then we're going to just get a bit of a bigger table. So that's with loop optimization. Yes. No. Yes. No. You get the idea. Okay, this is our little benchmark matrix. So what we're going to do is we're going to whip up some little shell script to run this benchmark, and then we're just going to get the data. We're going to make it record the data in CSV, and we're going to find some reasonable way to make sense of it. And we're going to run each one a few times, because there's a lot of background kind of variation with computers. Where computers are involved, things always become a little bit unpredictable. So we'll run each benchmark a few times, like 10 times or 20 times or something like that. So let's write the shell script, and then we'll set that running. And while that happens, we'll have another look at the code and maybe start prepping our pull request. And that's really what we want to get to in this session, is to get a pull request to the raptorjit repository with a little bit of benchmark data to show whether this is actually an interesting feature or not. Yeah, let's get into it. So let's say md5 bench.shell. what are our variables for version in v2.1 and sealed? Okay, so that's one for benchmark in MD5 no local. For loop in, let's just say one in which we enable loop optimization, which is actually the default, and another in which we disable loop optimization. Then for each of those, we just get, so what we want to get is CSV, and I tend to just I tend to use awk or something to get CSV. So actually, all I want to do here is write what is the test scenario. So we'll go like this. We'll say that's something that's going to be easy to pick up in awk. So that's going to just, every time it runs a test, it's going to print out the parameters that it's testing, and then I think we'll just run perfstat, and then we get cycles, and we get, I mean, perfstat gives you a few things: instructions, cycles, and ref cycles. They're all potentially interesting. So we'll just run perfstat, and then how do we have it in our shell to run the benchmark? We will run an appropriate version of the JIT, so we'll say, we'll assume that in the current directory we have a binary that matches the name of the version we're testing, and we will give it the appropriate loop optimization parameter. We will then run it on the appropriate benchmark. That could conceivably work. So let's just... Okay, so we need to... so I'm actually going to test two different Luajit binaries here, and what? So I mean, so what's going to happen when we run the sealed when we run the no local version with the standard Luajit, because we got these calls to jit.seal. So I just did a very, very simple defense against that. If we look in the I kind of wrapped all the table sealing in this if jit.seal. So if there is actually a function called jit.seal, so when this runs in a normal Luajit, that's going to be false. None of this is going to run. But when it runs in the one that we put our experimental optimization in, then this will run and the sealing will happen. So this benchmark is compatible with both versions. Let's try running this one. Let's be nice. No, that's not. Okay, so we need to provide the binaries, of course. So I already have from before a pristine Luajit 2.1. So let's copy that to be called v2.1 like this. And the current build, which matches our current source tree, which has the table sealing, it's the experimental one, will be called sealed. And then we have our two binaries. So let's try running the script again. And let's do it like this. And let's make it say that just so that if we would have several runs in the same log file, we can see how they're delimited. What could possibly happen there? Okay. So that's running. Okay, and then the only thing I guess that I'm lacking there is to give it more runs. Okay, so it already ran which is nice. But let's make it run 100 times because we need to buy some time so that we can look at the code briefly, and it's always nice to have more data, you know. So let's just say for run in okay, and let's put the run in there as well. So that we have something to differentiate our rows by. Maybe not necessary, but we do it anyway. We're gonna let that run just for about 30 seconds or a minute or something, and then we're just going to do a very brief sanity check on the outputs, just so that when we come back we'll have what we need. And then when we come back to this with the data, we're going to do a little awk script to turn into CSV, and then we're going to maybe we'll stick it in R. Maybe it'll be too simple. Maybe we just actually want to average. We'll see what we want to do. Log. How is it looking? Let's read the raw instead. So we're getting our. I shouldn't be running with the -x, but we can just grep that out later. We're getting all of our information. That looks right. It's run the v2.1 with the loop optimization on the normal MD5 no local. Everything seems to be getting a result. Everything's taking between nearly 1 second and 2 seconds. Everything looks kind of sane. Okay, so I think the benchmark's running okay. So let's hop over briefly, find the code. We're going to look at my. Well, actually, did I push it to raptorjit or luajit? Let us check. Let's look at it in Emacs first. Sealed tables. Okay, I think it's on my private luajit fork at the moment. And I haven't pushed it to GitHub, but I'll do that now. Well, I'll push that now. Although we're gonna move this over to raptorjit for our PR, but we may as well just look at this in the GitHub interface. Let us. Let us see what we have. It's only going to be one commit. Oops. Sorry, wrong base to compare with. One commit. This one. Okay. So what we have is in libjit. We have a new kind of primitive library function. The way that you implement those, excuse me, the way that you implement a new primitive library function is just you have this special declaration that there's a function called jit.seal, and then this declaration is going to be recognized during the VM build, and it's going to automatically define that. So when you call jit.seal, it's going to expect to get a table argument. It's going to error if it doesn't have one. And it's going to set the sealed flag on this table and then not return any results. And this sealed flag is something new that we've added in the definition of a table in the heap. And there's our actual instruction, but let's go down for a sec. What else do we do? When you allocate a table, we initialize the sealed flag to 0, and then we have our actual optimization, which is just this code here. So it's just that small amount of code that we added, right? So this is in the function that records a lookup into a table, and it's on the simple case where it was not resolved by a metatable and all of that kind of thing. So I'm putting all of that off to one side and not doing anything special in that case at the moment. So the way that this is implemented right now is that when you do a table lookup, it generates all the code for doing a hash table lookup, inline in machine code, and then at the end it says, but was the sealed flag set on this table that we just did a lookup on? If yes, then we roll back all of the table lookup code because we don't want to do that at runtime, and we just put out two guards. We do a guard, is this assuming that the table we're doing a lookup in at runtime is the same table that we were doing lookup in at recording and compile time, at JIT time, let's say, and is the key that we're looking up the same key that we did at JIT time. Under those conditions, if those guards succeed, then we will just use the value that we got as a constant. So we do the table lookup, of bitwise and or something like that. We do that table lookup at JIT time when we're recording the machine code, and then we don't generate any runtime code for doing that lookup. Instead, we just take the value and assume that it's invariant for the lifetime of the machine code. And so what is lacking here is any way to invalidate machine code. So if we would redefine one of these values if we redefine a value in a sealed table, then that would actually logically invalidate the machine code, and we need to implement that. So we need to add support when we do a table update to check if this breaks the seal, and if so, to flush the machine code and regenerate it. That code is not there right now, and I think that kind of makes sense because that's necessary for correctness, but first we need to actually see if the feature is actually useful, if it has any value, and that's the point of the benchmark. So is it actually worth going any further with? Does the feature actually do anything? It's important to get that resolved before we go in and kind of dot our I's and cross our T's. Another thing, just thinking about the semantics. So previously, I had wanted to make this a bit more fancy. I'd wanted to go in and say if a table lookup would actually turn out to be a very elaborate procedure, if it ends up being indirecting through several metatables, which might call functions and do all kinds of other stuff. There's a lot of stuff that can happen during table lookup in Lua, because table lookups are just defined very flexibly. I had wanted to roll back all of that and just put in a constant, but now I'm not doing that for like three reasons, shall we say? Something like, okay, the first reason is that it's tricky to implement. So the implementation that we have now is really simple, and I like that, and that's kind of nice, and especially nice to do some further kind of testing of the concept. Another reason is that if we take all of the funky stuff that can happen in a table lookup and turn that into a constant, then that kind of changes the semantics of programs. So that's not really a kind of a backwards compatible thing. So if you do a table lookup that calls a metatable that has some side effects, and we would replace that with a constant, then the unoptimized runtime program would have those side effects, and the optimized one would not. So we're changing the meaning of the programs, and in one sense that would be okay. We could just document it, and we could say that this sealed table is a use at your own risk, all the rest of it. And to a certain extent, I'm comfortable with that, because this is an experimental feature. The intention is to actually get experience with it before it would kind of be adopted and mainlined. But there's a lot of advantages, I reflect, to making the feature only affect performance and not kind of correctness. And one big one is for testing. So if we design the feature such that it should only ever affect performance and it should never affect correctness, then what that means is that we could go into the standard test suite that we have, and we could, for example, randomly seal tables. When a table is allocated, we could randomly seal it or not seal it, and we could see if that introduced any kind of functional differences, if anything changed in any of the test suite. And that would be really, really good for test coverage, right? I mean, we can do differential testing if we know that version A and version B are supposed to yield the same result. So that's actually very powerful. So I think I kind of like it on pragmatic terms. The implementation is simple, and the implementation is easy to test. I also kind of think that it's probably the right semantics to only optimize the simple case, because it does make it a bit simpler, and it does cover the main use case, which is just being able to refer to globals and and generally kind of like generally refer to tables that should be constant as constants and consider them to be constants. That's the main thing to give you that peace of mind, and that is actually accomplished here. So yeah, I would like to keep that simple. And another idea I just have rattling around in my head now is we haven't implemented the code for breaking the seal and flushing the machine code, and that is something that comes later. But something I reflected is maybe it would be nice that we only break the seal when you change the value in a table, not when you add a new value, for example. So if we would seal the globals table, we might reasonably expect that globals don't change their values very often, and that changing a global of the value of a global it's reasonable to have that flush the machine code and regenerate it because it's so infrequent. But adding new globals is actually pretty normal. Like when you load a module, it's often assigned a global name, and you don't necessarily want to flush your machine code every time you load a module, because generally in Lua code you often say require this module, require that module, and you kind of load everything a little bit piecemeal. So I think a nice semantics might be that when we do this recording in here, maybe we would be very careful that we only specialize the machine code when the sealed table has a value, and when the table has a value. So if there would be no value there, then we don't do any special optimization, and that would hopefully mean that when you add new values, that doesn't actually invalidate any of the machine code. The machine code would only be invalidated when you change a value. Therefore, we only need to detect changes to values and flush the machine code in those cases. Anyway, that's the brain dump on the functional side of things. So this is something that happens gradually. We do a few iterations of this change, and digressing a little bit again, the development model for raptorjit, which is the ultimate destination of this, is the distributed model like on the Linux kernel. So it's not that you have some great idea and you push it to master and suddenly everyone is using it. As things have happened in projects in the old days, it's much more of a kind of a percolation process. You have a great idea for a feature. You post it somewhere, for example, in a pull request to get some visibility. You do a few iterations to get to the point where it works and it's reliable, and then the next step is actually for somebody to use it. Like in Snab, we might take this and merge this over to Snab on an experimental branch there and test it, and if that works well, we might merge that into the main line of Snab on our local fork of raptorjit, and then we might come back to raptorjit upstream and say, hey, we've been using this for months, it's fantastic, it's great, and then that would kind of bring it to the main line of raptorjit. So the point here is that new ideas should spread, like memes. They should be merged to various branches, and the kind of the master branch is not the bleeding edge where all the latest and greatest things are. It's the trailing edge where all of the stuff that seems to have achieved some kind of a consensus goes. So that's the notion here. If you want the latest and greatest raptorjit features, you find them on their feature branches and you merge them in and you try them and you give feedback and you help them to be developed in a good way, and then when they're in a really good state and it's clearly the right solution, that's when they kind of go upstream onto the main branch. And you're never blocked from using a new feature just because it's not on the master branch, because you can always merge the topic branches. So there's an expectation that you're a little bit active in the process of working with the project, that you have your own branch, your own tree that you're pulling things into, which historically has been the way Linux and even ancient Unix systems before that, as I understand it. If you were back in kind of the ARPANET kind of an era or whenever, if you would get a new version of the operating system, you would probably get it as a diff and you would read through that and you would see which parts you were happy with and that kind of thing. You would have a kind of editorial role in maintaining your own local copy. So that's the mental model that I have for other people. Obviously not for everybody, but for people who are interested in trying out experimental features and participating in the development process and being close to the bleeding edge. Okay, now having talked a lot, we'll see if our benchmark is done. Is our benchmark done? Where's our shell? No, it's not done, but we're up to run number 88 out of 100. So we should have enough data at least to start writing to start CSV-ifying this. So let's just do that while we wait for the last 10% or so to run. So we already had our md5 bench.shell. Now let's write our md5 bench.awk. So what do we want to do? We want to, so every time, let's go to actual data as we do this. Is that what we want to cut out? Yes. That's just cutting out the debug printouts from bash. So this is what we're going to take into our awk script, and we want to kick out CSV. And so these are all going to be columns in the CSV file, and we'll also pick out a couple of we'll pick out a few of these as well. We're probably only interested in cycles. It's a pretty reasonable choice, but we'll pick up maybe instructions and time as well. I'm running this on a beefy machine. It's got like a dozen cores and nothing else particularly happening, so I don't expect that there's going to be any significant contention for the CPU here. So I think we can take cycles. Cycles and elapsed time should correlate very well. I hope that I have turbo boost turned off. I usually do. Anyway, if there's any variations there, we should see it because we ran 100 tests and everything should even out. That's nice. When I do benchmarks, I normally run it on a dedicated machine with a bare metal machine that doesn't have any hypervisors or anything else sharing the load, and I usually turn off the CPU turbo boost kind of thing because it's a little bit unpredictable and sensitive to other things. But I also run a lot of tests, like 100 tests here, so that if there is anything confounding, like if the CPU turbo boost is enabled and this is sensitive to the temperature of the CPU, and it throttles a little bit for thermal reasons or anything like that, I always find it nice to know that we're gonna have that accounted for. Anyway, let's write some awk code and stop saying blah blah blah. MD5 bench.awk. We want to match on, when we see this line with run, then we want to say run is the second field. So if the first field, or if the line matches at run, then we assign the run variable to 1. And likewise, so we pick up all of those, and then when we pick up this cycles, I'm going to say cycles is, we're going to need to do some, we're going to need to strip out those commas somehow. I don't have it in my head how you do that in awk, but we'll take that later, because otherwise the commas, of course, will be problematic for a CSV file. Maybe we can even ask, well, it's too late to ask perf to take those out, but we'll do that in some simple way. We'll take the number of instructions, because it can be interesting. Actually, being able to look at the number of instructions and compare the instructions per cycle is actually interesting and relevant for this, for CPU microarchitectural reasons that I would actually really love to take a quick look at. I don't know if we'll do it in this session or a bit later, but it's a very interesting thing that a lot of the hash table lookup work that is being eliminated is a lot of code that does not, that it's code that does not contribute to the kind of the latency of the main flow of control. So it's code, a lot of the hash table lookup code is just checking guarded assertions, which is a control dependency and not a data dependency. So in principle, the CPU can execute the guards and the real work in parallel, and they don't necessarily have to slow each other down. So it's actually a kind of a important thing when making this optimization to keep in mind what is the value proposition. So we might eliminate a lot of instructions, but that doesn't actually necessarily do us any good if those instructions were not contributing to the overall latency of the code's execution. So what I think is there's so many of those instructions that they will create a throughput problem for getting all the instructions executed by the CPU. So it's going to bog down and create contention in CPU backend resources. And that therefore, when we eliminate these instructions, that it will actually improve program performance. And this benchmark will kind of be a sanity check on that. And then we can also look at what that means. And we might see this reflected here. We might see that the ratio of instructions to cycles, the number of instructions retired per cycle on average changes in some interesting way here. Anyway, I digress. More awk. So now we've picked up a lot of things, and the last line is this seconds elapsed. So when we see a line that says seconds time elapsed, we're going to do two things. First, we're going to say that seconds is the first parameter, and then we're also going to kick out our CSV line. So as we go through these lines, we just update our variables, and then every time we get to one of these lines, we're actually going to emit a line of CSV. So we're going to say, well, let's also pick our file format. So we'll start off by kicking out a header line for our CSV, because that will make everything easier. We will do run version benchmark loop cycles instructions and seconds. That's our format. So now we need to match that down here. We need to output the run, which is a number, benchmark, which is a version, which is a string, benchmark, which is a string, loop, which is a string, cycles, which is a decimal number, instructions likewise, and seconds, which is a floating point number. And then we need to fill those in. Run, version, benchmark, loop, cycles, instructions, seconds. Something like that, right? That doesn't look so bad. That doesn't look so off. The problem we have here is we're going to get commas in some of these fields, but we'll see if this works first, and then we'll come back to that. First, let's check that our thing has finished. Yes, it has. Okay, so what about if we would say run that on the log and see what happens. Oh, okay, you can't actually use end like that, can you? I'm not going to deal with that right now. That is what comes out. How plausible is this? Not very. No. Anyway, so we didn't get sensible values here. Like the runs looks good. This looks good. Runs is good. The software version is good. The benchmark name is good. The loop optimization is good. But then what's this? We get 1 and 3, and we get zeros and stuff. So we're not picking up the instructions and the cycles in a good way. So this. How do we get 0 for instructions? Okay. I think that's these commas. So when we assign instructions here, it's becoming a string, and then when we try to print it as a decimal, there'll be some awk. We'll do some kind of do what I mean kind of a conversion to a decimal there, which won't do what we want. I mean, if what we mean would be to strip out the commas. Yeah, so there it is with the commas in all of their glory. But what we need to do actually is we do want to print it as a decimal, but here we want to strip out the commas. So let's Google for how you do that. Awk remove commas from numbers. I somehow think we're not going to be the first people to want to do this. G sub commas with nothing. Okay, let's try if we would just say globally substitute commas with nothing. I think that would be to all of our inputs, so it's a bit blunt, but that might do the job. Turn all of our commas into nothings, and then do what we want to do anyway. Just align those as I want to do. What would happen if we did that? Could that possibly have the right effect? Yes and no, right? So now we've got plausible looking values for cycles, not so much for instructions though. Okay, so what did we do wrong, especially wrong with instructions? Did we spell that the same way both times? Yes. Is it spelled the same way over here? Yes. But not spelled the same way there. What about now? Okay, now we have plausible looking values for everything, so that's a bit better. So now we have a CSV file that kind of looks like should have our answers to all of our performance queries inside. So why don't we take a small 5-minute break, warm, and do a small context switch on our brains. We're just going to pull this into R. So I mean, I don't want to overdo it, but there are a few different angles that it could potentially be interesting to look at this data from. We might want to, but we want to look at it from a couple of angles. Even if in the end we might be able to summarize everything just with a couple of averages or something. I always like to be able to kick things a little bit. So we'll take a break for 5 minutes, and then we will we'll come back and whack this a little bit with our R stick. Here we go. Back in a sec. here we go again. Sorry, we had just run our benchmark on the sealed tables optimization. We did a few different scenarios, ran each scenario 100 times. We kicked out a log file. We wrote some awk code to convert that to CSV, and now we're going to look at the CSV file. So let's do that. I just pulled up our studio, and I've just copied the file across to this machine. So now we should be able to say that our data goes to read CSV. No, that file does not exist. Oops. How about that one? Yes. Let's take a look at that to make sure the format worked. This is our CSV data. We get the run that we had, we get the version, we get the benchmark, whether it was the original one that, I'm just going to briefly pull those up again, just to get our context back. And what we're comparing here in the benchmarks is on the left, we're comparing the MD5 benchmark that goes through and thinks about every single library function for any module that it might call ever, and declares a local variable to shadow that in so that it can get all of those function table lookups done at the beginning, which I find provocative, which I've already complained about enough. On the other side, we have the MD5 no local version, and here we just took away all of that, and when we want to call a function in another module, we just do that. We don't care. We're wild and crazy. We say, I know that according to Lewis Semantics, writing bit means going out to the global variables hash table and doing a hash table lookup to get bit. And I know that once we get the bit module, we need to go in and we need to do a hash table to get the XOR. But that's Lewis Semantics. We're going to expect the compiler to fix this for us. And now the benchmark is going to tell us to what extent that happens. So let us swap back in a bit of R. Every time I hop between tools, it takes me a little while to warm up my brain again, remember which way is up. So you'll forgive me, I'm sure. What do we get when we just ask R for a summary of the data? Let's plot the data to start with. Visual is always good when we're kind of trying to get our thoughts in order. So if we ggplot the data, and we'll think about the aesthetic we want. So we're going to go. We're going to have. Let's start off with a geom jitter, which is going to be like a. It's going to be. We're going to plot individual points for each of the 100 tests for each of the brands. We're going to get an individual point, and this is just going to let us see how messy, noisy things are, which I want to see in the beginning. We could also do like a box plot or something, but this will be very raw. For every data point, we're going to get for every data point, we're going to get a circle or something drawn on the screen, and the x value, because this is a jitter plot, so the x value is going to be chosen at random just to spread things out, and we need to say that we want the y position to be, let us say, the number of cycles, or let's just say the number of seconds. Sorry, I have those backwards. The y is, do I? Hold on. Hang on, for a jitter plot, shouldn't the x be for jitter plot, shouldn't the x aesthetic be always be random? Why do you need an x aesthetic for geom jitter? Okay, let's give it an x position. Let's say x is the run. We'll just do them left to right in that case. Okay. So anyway, this is without any differentiation for any of the software versions or anything like that. This is just the data plotted. So we see anyway that there's like 4 different performance levels basically, well at least. And what we need to do is now tease out things a little bit. And I guess we can see that the scale doesn't go all the way down to 0 there. So it's maybe a little bit hard to compare. Why don't we try and fix that as the first step? Why don't we say scale y continuous? Do you say minimum? How do you do it? How do you do this in? That did not seem to work. Can you put it here? I might be going off on the wrong. That worked. Okay, that's nice. Okay, so I think it just keeps us a little bit grounded to have the y-axis starting at 0. I don't think we needed that one there to get it. So yeah, the y-axis is the number of seconds that it took for the benchmark to run, and this is the run number, and we just plotted everything over the top of itself now. So what about if we would say that the color is going to be according to the software version? The color is the version. There we see. There we start to see a bit of a picture. Okay, we need to get more details, but we'll just do this a piece at a time. So the slowest version, the one that took the longest time, was from the v2.1 branch, and the sealed branch, its worst case, was significantly better. So I'm thinking when we dig in, we're going to find this this was something beneficial. And what do we see down here? There were some other versions that ran, and the sealed version was faster than the v2.1 version there as well. So this looks kind of promising, right? It kind of looks like this amongst our scenarios. There's a couple of different cases, and the sealed one was seeming to do better. But we got to tease this picture out a little bit more within the confines. Can I make? Hold on. Get a bit more space so we can see things a bit better. Hey, let's. Okay. Is that going to be better? Let's just see. There's some kind of a compromise on the 720p screen size here. Okay. Now let's split things out again. What else do we have? We want to see whether loop optimization is enabled or not. To start off, let's just do that as a shape. Is it called shape? I can't remember. Shape is the whether the loop optimization is on or not. Does that work? Yeah. So now we have colors and shapes, and the circles are when loop optimization has been disabled. The triangles, I mean, it's a bit small to really see this in any kind of a satisfying way, but the triangles are when loop optimization is enabled. So these are the circle, the high ones are the circles. So this seems to be a comparison between the sealed branch and the v2.1 branch in the case where loop optimization is disabled, because they're circles, and here it's okay. But another very interesting and very important variable that I'm not accounting for here is which benchmark we're running, whether it's the, you know, we're going to struggle to see everything, to map all of our interesting dimensions onto visual aesthetics. So you know what? I think we're going to take this actually in 2 steps. First, we're going to take the thing that we're most interested in, which is to just focus on the case where loop optimization is disabled, because that's the one I think we're going to have the biggest effect in. And once we've seen that, then we'll sanity check the other one. So I'm going to filter this data to the cases where loop is minus loop. Those are the only ones that we want right now. Okay, that simplifies things a little bit. So now what we're comparing is only cases where we're not doing loop optimization, so we don't need to use that shape anymore. We could use the shape for something else now, because we know that everything is loop optimization off. And I think we see the shape of these points, we see that they're fairly consistent. The spread is not that much. We don't have a wild distribution like all over the shop, so I think it's quite fine to summarize this with a box plot, say, instead of looking at the points all the time. So let's do it like that. But we lost our y. How did we lose our y min there? We had this thing was doing such a great job for us. To put it there. Do we say again scale y continuous limits equals okay, add to a bit of work there. Okay, so this is so there was a bit of a spread on the v2.1 and not here, and I guess this was obscured by the way that we were drawing things, so we saw like a lot of red dots and there were probably some blue ones underneath that. So I would imagine that this spread that we see here is because of some factor that is in our CSV data. It's just something we haven't put in our model yet. So what was it that we missed up until now? It was which benchmark we're running. Are we doing the no local one, or are we doing the normal one? Let's put that in as can you write in ggplot, can you say that you want the color to be the version combined with the benchmark? No. And let's do a concatenation of them instead. And let's get our syntax right there. Deep breath. So what do we got? These three are all about the same. This one is slow. So what is that telling us? The slow one is when we run the v2.1 branch with the no local benchmark. So okay, so the most important thing that this graph is telling us is that when we run the normal version of the JIT compiler with the version of the benchmark that we changed to take out those local declarations, then performance degrades considerably. So what that means is that that all of this work here to take all the library functions and cache them in local variables, this is when, and again the data we're looking at here is only the cases where loop optimization has been disabled. So in that case, this is very important actually for the normal working with LuaJIT. So this is one of the standard LuaJIT benchmarks, and the way that it is written with this stuff is actually tuned for the normal LuaJIT. So it's not, people have not just been doing this for fun. This is not some kind of a cargo cult kind of a thing. This is actually an effective programming style to get optimizations. At the same time, we can get the benefit with the sealed tables feature. So the sealed tables feature is working as designed, this is saying, because when we run this no local declaration version with the sealed branch, then the performance is actually quite good. Looks like it's not quite as good, but it's very close. So and I think that at this point that scale is doing us a disservice. So let's let the scale be just zoomed in on the area that we care about. Yeah, so what it's saying is that it's when we run with the no local declarations on the sealed branch for our current prototype of the sealed tables feature, there is a very small but measurable difference, a bit of overhead compared with the local variables. So if you actually cared about a very small amount, we could do a Tukey's test here to get a confidence interval for the exact level of difference here, but I feel like that would be kind of overkill right now because it's really small. I'm happy to say it's really small right now. So when I look at this graph, I say that for this data set, which is our benchmarks with the loop optimization disabled, only including the data when loop optimization is disabled, what it says is it is actually okay to program in that style without caching things in locals when you have the sealed tables. Sealed tables works. If you've got it, then that's fine. This, I don't think this is going to be a meaningful difference, whereas this is a very meaningful difference. So this is what you want to avoid. And you know, one way to do that is to cache everything in locals. The other way is to use sealed tables. So I'm very, very, very happy and encouraged by this graph. And maybe this is the graph that we're going to want to put on our pull request to explain the value proposition for this change. Having said that, now let's look at the case where loop optimization is used. So if you have loop optimization, then does the difference disappear, or is it lessened, or do you actually get a regression from the sealed tables? What is it that happens? So now when we filter, we just take the cases where loop optimization is there. So we're going to see the same graph, but for the loop optimization case. Aha! It looks the same. You know, there's a little bit more spread for reasons I don't immediately know, but the very, 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 very interesting thing here is that these ones all look basically fine, whereas, as before, if you run the version that doesn't have the local caching and also doesn't have the sealed tables, then your performance is bad. No, wait, hang on, sorry. There's one big difference, is that the scale is different here, right? So hang on, let's repeat this comparison with the scale fix, because I think the difference actually here is much less. Visually it looks the same, but I'm fooling myself, which is very easy to do when you're just mucking around, which is why, of course, you do use things like two-keys test, and you do actually always look from multiple angles. But anyway, for now we're just going to play it wild and crazy and just keep poking around. If we make a mistake, these graphs are going to go onto a pull request. Someone's going to say, "Hey, that's, you know, you goofed that." So it's not, you know, it is not a life and death situation. Now I want to look at the original graph that we had before, and I want to get that again with a fixed scale on the y-axis, going up from 0 to 2. We'll say. And now this is something we can then compare with, let's facet it as well, shall we? We don't have a huge amount of screen real estate, but I think we'll get away with it. We'll show both graphs side by side instead of flipping back and forth between them, just for the sake of making things a bit simple. We want to see, or no, we want to say facet wrap. And we want to see the results explained by the version. No, by where the loop optimization is used. So we're going to get two graphs side by side, one for the loop optimization case and one for the non-loop optimization case, which means we don't need to filter this anymore, because we can have all the data in one place. There, that's a little bit more like it. So here is the case where loop optimization is disabled. So what we see here is that, comparing these, loop optimization helps a lot on the MD5 benchmark in every scenario, whether you have the sealed tables turned on or not, which version you're using or not. So that it always takes everything takes longer with loop optimization disabled than with it enabled. So loop optimization is a great feature, and there's no contesting that. It's a very, very great feature. That's the first thing. The second thing is that it's always worse to run this this modified version of the MD5 benchmark that does not do a lot of local caching. It always performs worse when you're using the standard LuaJIT, but not when you're using the sealed tables. Okay, very, very slightly there, but to a first approximation, there's no bad cases if you have sealed tables, whereas if you don't have sealed tables, then it's very important, or it's important to cache things in locals. The third thing that we can notice is that the impact is much bigger with the loop optimization than without. So this is something I'm happy to see. I'm glad to see. I want the sealed tables optimization to be overlapping and partly redundant with loop optimization. So here we have this wonderful, huge effect from using sealed tables. comparing this with this. When you enable loop optimization, a lot of that effect disappears, which means that a lot of the performance gain we're getting from the sealed tables is something we also get from loop optimization. They're mutually redundant, and that's really good. I want raptorjit to have lots and lots and lots and lots of mutual redundancy, so that you never ever depend critically on any one optimization. You have a lot of different optimizations, they're overlapping, some of them will kick in sometimes, some of them will not, and it will all kind of come out in the wash a little bit and average out. So then as an end user, the perception will be robustness. As an application programmer, your code will be working consistently fast because you're not massively dependent on any one very specific optimization. You're kind of covered. So that is what I perceive as a weakness in LuaJIT, that maybe your code is lightning fast with loop optimization and dog slow without loop optimization, and I want to narrow that gap and make everything more kind of everything should be closer. Each optimization should contribute less in itself. There should be more redundancy, much more redundancy. Anyway, I rant. This is a nice picture. I think the next step is to make a pull request on GitHub, just summarizing in a couple of paragraphs everything that we talked about here today. What is the table sealing feature? How does the implementation work? What's missing from the implementation? How does it look in initial benchmarking to prove its value? And what are the next steps? What needs to be done before this would be something you could really use in practical programs? But I'm pretty satisfied for now. Actually, this feels like this was a pretty nice live coding session. I'm quite comfortable. It's quite fun doing little bits of awk hacking, doing little bits of R hacking, doing little bits of compiler hacking, and that kind of thing. I'm not sure if live coding will be as much fun with like composing pull requests and thinking about the right words and going back and forth and editing. We'll take that another time. I would like to build up my own kind of comfort level so that I could just stream my whole kind of working day, and of course you can always just hop away and skip over and everything. But for now, I'm going to say that's good enough for the moment, and hop off the stream. So thanks very much for joining me on this, and we'll do a pull request out of this, and then we're actually not in any kind of a hurry. Then it might be this might be a feature that we can come back to in a week or a month. Let our thoughts go a little bit. We'll see. It feels like we're coming to a good point, a good kind of punctuation point here, a comma mark in development of the sealed tables feature for raptorjit. So done. Thank you.